In this video, we'll look at the average rate of change idea, but in the context of a polynomial function. Um, so the average rate of change formula is the same formula as it was for a linear function, but in this case, our function f is going to change to, for example, maybe the function f of t is equal to t squared minus t. This function here can be anything. Okay, so the average rate of change idea applies to any function. I just thought this would be a good example to illustrate the idea. Okay, so again, for example, notice that when you're doing the average rate of change idea, you need to pick two rows of the data to look at. So for example, looking at these two rows of data tells us that the average rate of change of this function y of t is equal to t squared minus t from the value t is equal to 1 to t is equal to 1.5. We need to compute the y value at 1.5 minus the y value at 1 divided by 1.5 minus 1. Filling in the values from the table, the y value at 1.5 is 0.75. The y value at 1 is equal to 0, and then subtracting 1.5 and 1 is 0.5. That leads to your answer for the average rate of change on this particular interval of 1.5. Okay, so one can compute the average rate of change of any function on any particular interval, and it would just require two sets of data. So here we could say that the average rate of change of this function f of t on the interval t is equal to -1 to t is equal to -0.5. That answer, if you compute the values out, would be -2.5. Okay, so those are the numbers. What we are seeing in terms of graphical, in a graphical sense, is that before we were looking at let's say we were looking at these two values, these two rows, and we're trying to compute the average rate of change idea. Okay, the average rate of change from a value x is equal to, or t is equal to 1 to t is equal to 1.5. So here's t is equal to 1, here's t is equal to 1.5, which implies that our delta t is equal to 0.5. What we need to compute now is delta y. Delta y is the change in these y values, so that'd be 0.75 minus 0, which is 0.75. Okay, if you take these two numbers, delta y over delta t, the delta y you computed was 0.75, the delta t is equal to 0.5. Divide those two and you will get 1.5. What we're seeing in the picture is the rate of change between these 2 points. So right here there's a little slope of a line, okay, and the slope of that line is 1.5. Okay, if we go between these two values, so find the average rate of change of this particular function, t squared minus t, but compute the average rate of change from t is equal to -2 to t is equal to -1.5. The answer you're going to get is -4.5. What we're seeing there is the values t is equal to -2 and t is equal to -1.5. Therefore, delta t is equal to 0.5. The change in the y values, right? Here's the y value for one of the points, here's the y value for the other one. So the change in these y values is 6 minus 3 3.75 minus 6. Okay, and then if you divide the delta y divided by delta t, the 3.75 minus 6 divided by 0.5, the answer you'll get is negative 4.5. That negative 4.5 tells you that there is a line here between these 2 points that has slope negative 4.5. Okay. So what we're seeing here is an example of a function. Right? It's relatively easy to compute values of this function, which is why I've chosen it. But it illustrates the idea that the average rate of change between of a function on a given interval can be different values. So here we're seeing that the average rate of change is negative 4.5. Here the average rate of change is 1.5 because the slope of these lines are changing. So if you go the average rate of change, the slope of the line between negative 1 and negative 0.5, the average rate of change should be negative 2.5. So the slope of this line is negative 2.5. Okay. From 2 to 2.5, the average rate of change between 2 and 2.5, the average rate of change will come out to be 3.5. That would be the slope of this particular line. So it makes sense that for different functions, the average rate of change can be a different number because the function is changing and it can be changing differently on different intervals. So that is the average rate of change idea in the context of a polynomial function. Our next video will discuss the average rate of change concept for an exponential function.